All right, hey everyone, this is Chemistry 30, History of the Model assignment. I am going to be working through the fill-in-the-blanks that you have in front of you. If you don't have that fill-in-the-blank document, I will encourage you to go here to mrmathwell.com and History of the Model Atom Assignment Blanks. It's right here on the Chemistry 30 page. You can download that and follow along with me. All right, without any further ado, let's talk about the earliest historical model of the atom that we know of. And your blanks will look like this. Greeks placed, the ancient Greeks placed a very high value on knowledge. They determined that through observation and careful logical thought that patterns could unlock the mysteries of nature. They focused on philosophy instead of on deductive experimentation. So just as you're completing those blanks, let me fill in the blanks a little bit for you here on that. So the Greeks did more or less philosophical reasoning was how they arrived at their facts instead of actual physical experimentation. And I think the big reason for that was there were so many factors involved, so many variables. It was hard to control everything. And so the purity and rationality of thought, A leads to B, which leads to C, which leads to D. If you can't philosophically debunk any of those steps, then A leads you to D in that way. And so we do things a bit different now, and we do experimentation heavily instead of these thought experiments, or instead of just relying on our logic. So as I said, they did not place value, or as much value as we do today, on experimentation due to the imperfect nature of human action. They thought in absolutes. And only relied on these thought experiments. So I have talked to you a little bit about this just now. And the other thing is, of course, how do you control all of the factors from one trial to another? They just thought that was, and of course they didn't have the technology back then, right? And so rationally using their mind, they thought was the purest way to get at scientific truth. The earliest model can be best described as something called the Hooke model. And this model was the prevailing model in early times. Each atom would combine with other atoms by literally hooking onto other atoms, and in this way they became a substance. So you would have something like this, this atom has this series of hooks, and you have this other atom which has, some different kind of hooks and whatever it is, and they just kind of bump into each other, and they become this entangled sort of, the hooks kind of hook onto each other, and that's how they become a substance sort of thing. So that was one of the earliest models that we know of. Substance. Democritus was credited with this theory. So one of the earliest theories of the atom, he coined the phrase the atom as well, being Greek. And this was the Hooke model. Many thousands of years later, John Dalton came along, and in between that gap, there wasn't really a whole lot of advancement in the area of science. And of course, once we started knowing more, having greater technology and doing a little bit more experimentation and getting at things a little different way, John Dalton, who was a teacher, he came up with some important points in his atomic theory. So here are the main points of his atomic theory. All matter is made up of atoms. Atoms are indivisible. Now, again, this is not necessarily current atomic model belief, but this is what he came up with. He thought that these atoms were like, hard, steel balls kind of thing, and that they couldn't be penetrated or split up, that they were indivisible and indestructible. And this is where, our current understanding varies a little bit from what he originally had thought, right? Because we know there are subatomic particles in atoms. All atoms of a given element are identical in mass and properties. Largely, we feel the same way. The atoms of an element are identical in the number of protons that they have in their nucleus. Their mass, because of isotopes, now can be a little bit different. But he said all the atoms of a given element are the same. Compounds are formed by a combination of two or more different kinds of atoms. That's largely exactly what we believe today. And a chemical reaction is a rearrangement of atoms. So there's nothing being introduced, nothing created or destroyed as far as the atomic level. It's basically a shuffling around, an exchange of different atoms to form different compounds. Again, largely what we believe today. So there are, you might see in your textbooks more points from Dalton's atomic theory, but I've condensed it to 4 for you. All right, Dalton also developed the law of multiple proportions, which still stands today, by studying and expanding on the works of Lavoisier and Preux. Dalton noted from percentage composition, and that is the composition means what is it composed of. So the percentages of tin oxides, okay, that were actually the tin part and what was actually the oxygen part. He figured out that when they combine, they always combine in a certain ratio. And that ratio is a 1:2 form. So that 1:2 ratio, he thought, well, that's interesting that we always have a kind of whole number ratios that it boils. No matter what sample size you take, those same ratios hold true. And so because they were whole number ratios, it strengthened the idea of some basic atomic unit in chemistry. So you think about it, if you have an atom that's indivisible, only one of those can combine with another atom, and if there are more than one, they should be whole number ratios. And so that's what he found. That's the law of multiple proportions, strengthened the idea of the atom as the base unit in chemistry. Okay, so from the original early models and Dalton's model, we moved to Thompson's model. So Thomson came along and conducted something called the cathode ray tube experiment. Now, of course, in chapter 4 in your textbook that we're using, Glencoe Science, you're going to be able to read about and research more about these landmark experiments and the scientists. So I would encourage you to read a little bit of background. This is, of course, just the notes from my class that in case you missed the class, you can fill in the notes here. And this is just a brief little background about how this model progressed. So I would encourage you to read it. You'll notice that there are websites that I've also put up in these notes that you can do some further exploration. So he conducted his cathode ray tube experiment. He was investigating cathode rays, which were glowing beams of light particles, or so it was thought. He named negative charged particles inside the cathode ray tube as corpuscles. Corpuscles. These later became known as electrons. So it was Thomson that discovered that, hey, we have this negative characteristic inside these light rays, or these cathode rays. And it was quite interesting to know that there was a characteristic such as this in the atom. Thomson's model of the atom consisted of positive and negative parts of Dalton's spherical model of the atom. So Dalton, remember, thought that the atom was indivisible. There was nothing inside, and that it was all sort of uniform in composition. Thomson came along and said, you know what, I think there's actually different parts inside the smallest unit, the smallest atom. And so that was quite groundbreaking. These results were controversial because it was generally accepted that atoms were indivisible, as Dalton hypothesized. Further exploration was required on the parts of the atom, and so because there was these different characteristics, there was certainly further exploration that was required. Since there was a negative aspect that Thomson had discovered, others wondered if there were any positive parts to balance off the electrons. And so in Thomson's model, you will see that there are negative and sort of positive parts, in a sense, but not much was known about those parts. We now understand that the electron has virtually no mass. It exists outside of the nucleus, separate from the positive part, and not intermingled, as he thought. So Thomson's model of the atom, we're not going to talk too much more about that. So Thomson's model of the atom was called the Plum pudding model. And the reason, he was English, the reason why he was the plum pudding is because there was little bits of these negative parts inside of the atom. And it was sort of understood that the mush, the rest of it, was sort of this gelatinous sort of positive mush. And so these negative parts of the atom were kind of seem to be like little bits of plums in this plum pudding. So you have like let's say you have like a vanilla pudding. Okay, it's uniform throughout, and then if you put little bits of raisins or plums or fruit in there, you have this pudding with distinguishable pieces inside floating in amongst the mush. And so that's kind of the way he envisioned it. The negative parts were separate from the sort of the positive mush. We called it the plum pudding model. Plum pudding. Oh, and this, let's see, this color is almost purple. And it's kind of blue. Okay, fine. Purpley color. Not really. Okay, section 3. Rutherford Bohr and the atomic nucleus. So as the model of the atom advanced, in 1908, Ernst Rutherford's gold foil experiment emitted beams of alpha particles, and those are positive particles, through a very thin sheet of gold foil. He expected to see the larger, fast-moving positive particles completely blast through the foil like a cannonball would blast through tissue paper. So this thin sheet of gold, and I'm talking about thin, like just number of atoms kind of deep, and it was kind of like shooting a bullet through a piece of Kleenex, right? And so he thought that it would just obliterate this gold foil. But what he found was very, very surprising. So remember, we have these large positive particles screaming, careening towards this really thin sheet of gold foil. And it was thought that this would just kind of, just blast right through, right? And just kind of explode this tin foil and it would just keep running through. But surprisingly enough, Rutherford found out this. Surprising to Rutherford was the obviously formidable part of the atom that the positive particles encountered as the alpha particles were unexpectedly deflected when passing through the foil. So imagine if you shot a bullet from a gun through a piece of Kleenex and the bullet bounced back. Okay, that's the same sort of surprise that Rutherford, who studied in Canada, by the way, worked in Canada for a little while, that's the same sort of surprise that he discovered here. So instead of this cannonball passing through this tissue paper, in some cases this cannonball would deflect, or in some cases bounce back almost right back in the direction that it came, and it was just unbelievable. This changed very much Thomson's theory of a uniformly positive and negative pudding. Okay, so again, Thomson thought that it was just kind of this big mush with these little plums in there, and so the positive photon should have blasted right through this relatively meek positive mush. But Rutherford envisioned, because of this experiment, he envisioned or deduced that there must be some kind of very small and dense and very positively charged region inside each atom. And so for a positive charge to be deflected almost back into the path where it came, it would have to encounter something very formidable, and a like charge would repel that. And so he figured that there were, inside these atoms, there were small pockets of very dense positive charge that would have repelled this this particle, right? The alpha particle. So this provided a specific space for the positive charge, a specific space, and not scattered evenly throughout the atom, as Thomson envisioned. So Niels Bohr, Danish physicist, came along and hypothesized or guessed that the orbits of electrons outside the nucleus were based on his mathematical calculations. So we went from, this is what we got we went from Hooke's, right? We went to Dalton, solid steel balls there. We went to Thomson, where we've got negatives kind of scattered throughout. And now we've got Rutherford, okay, where there's a big positive kind of part with maybe some electrons scattered throughout somehow. And then Bohr came along and said, you know what, I think that there's a nucleus, and then there's specific orbits where these electrons will fly around. And this is sort of the traditional atomic model that you see, right? Kind of like this, from the 60s or whatever. And that's what kind of Bohr hypothesized. He said, no, I think these electrons are kind of flying around in specifically mathematically determined paths. And that was pretty huge. So you can see how the development of the atom is coming along here so far. Okay, 2 more sections left. Robert Millikan's oil drop experiment. All right, so we need to find out a little bit more about electrons now. We found out a little bit more about the nucleus, the positive, dense region. So this was work that advanced our knowledge of the electron. In 1913, Robert Millikan used charged metal plates to create a magnetic field. He then injected a fine mist of oil into the electric field and calculated the force required to suspend the droplets. Okay, so think about this. We've got a charged field here between 2 magnetic plates. There's oil sprayed into it, and the varying of the charge of these magnetic plates could actually prevent the oil spatter, the mist from falling. It could kind of levitate it, okay? And so there was these atoms of oil were reacting to this magnetic field. He then was able to calculate the charge to mass ratio of the oil droplets. All right. So there was a charge that was able to be repelled by this magnetic field. Using his data, he was able to find the smallest common charge to each trial, which led him to the charge of a single base negative electric unit, which is the electron. So again, the different masses of oil that he injected into his experiment here varied with the charge to kind of like levitate sort of these particles. And when he put in more, he had to put more charge, crank it up. And when he sprayed a little bit less, he had to dial it back. And when he took a look at all of those ratios, he was able to say, okay, there's like a base or a common sort of lowest common multiple, and that must be the charge of a single electron. This experiment supported the theory that the electron is negatively charged and is the negatively charged particle inside the atom. Determining that there is a specific negative charge in the atom confirms the existence and the theory of the electron particle. All right. This experiment determined that there was a specific charge for the electron, therefore giving the electron a specific set of characteristics and opening the door to calculating charge for protons as well in the atom. Okay, so Millikan further work on the actual sort of charge of a negative electron. And yes, there's more work to be done at this point on the proton, the nucleus, the orbits, all that sort of stuff, and that's being developed, as we speak, I guess, but in the next section, you'll see in section 5 where that really comes on. So electrons, it was determined, are not scattered throughout the atom, as Thompson's Plum pudding model hypothesized. Instead, they are separate from the nucleus. So at this point, they named the nucleus as sort of this central positive region, and the electrons are separate from the nucleus and the positive charge. Electrons also can flow from one atom to another and do not occupy specific orbits but regions around the nucleus. So taking from Bohr's model here with sort of the electron orbits like this, we now know, yes, there's a nucleus, yes, it's positive charge, yes, the electrons are negative and they do kind of fly outside the nucleus. But now what we're going to look at here in section 5 is sort of a new model and more or less our current model of the atom, where we have now regions, so these three-dimensional sort of regions of space around a nucleus, but regions of space that electrons with certain amounts of energy can actually occupy. So let's just get into the notes here. I'll explain more as we go along. So not specific orbits. So let me just, let's just say, let's say you have a park, right? If you have a park and you have a path that goes around the park, and there's children in the park, and you ask the children to go play, Bohr thought that all the kids would walk on the path, okay? All these electrons walk on the path. They would walk on the path. But it's been found out now that, you know what, the kids kind of play all over the park. So they can be on the path or they can be inside and all around, but still inside the park. You might have one kind of try to get away, but most of them are inside the park. And that's sort of the model that we're at now. And so you get these regions where the electrons are playing. So section 5, let's complete the notes for section 5 then. Marie Curie, Henri Becquerel, and radioactivity. Becquerel discovered the radioactive substance of uranium. He discovered radiation was emitted from potassium uranyl sulfate, this one right here. So radiation, okay, so radioactive radiation, this is energy that's emitted from the nucleus of an atom. Let's further explore this. Becquerel placed his potassium uranyl sulfate compound onto photographic plates. So they would respond to light and energy and by making sort of a mark. It's how cameras used to work with the camera film. You know, back when I was a kid. Actually, it wasn't even that long ago. But you had a camera and there was a roll of photographic film inside there, and so you had to kind of like click or it was automatic now, and you take a picture and all of a sudden you hear this, you know, and it actually rolls, the rolls move, and this new photographic plate comes where it lets the light in and then you capture the picture, right? Seems so old now. Now we just pull out the phone and just go click. Not so. So anyway, so he had some photographic plates. He covered the plates with black paper to protect them from light. Okay, so no light was getting in to make marks on this photographic paper plates. But instead, he put them on his windowsill so that the uranium compound could absorb light and begin to glow. So this uranium compound would absorb light. Dangerous stuff. They didn't know it at the time. All this radioactive material. Whew. Actually, Marie Curie paid a pretty painful price for it. She did a lot of work with radioactive material. It was said too that she would have a vial of like glowing radioactive stuff, and she just carried it around in a pocket, you know, and just like show it off. And anyways, she died. I think she died a pretty horrible death. Radiation poisoning. Anyhow, back to the notes. As he expected, the rays from the phosphorescing uranyl sulfate penetrated the paper and exposed the photograph, and even penetrated metallic objects as well. So in his test, it wasn't the sunlight that was making the photographic plates react. Instead, it was actual energy coming from just this substance that he had kind of hidden underneath there, inside, which was amazing. So he was able to detect this energy release, which made a mark on these photographic plates. He also noticed that it did penetrate even metallic objects as well. So this is some pretty wild stuff that they were uncovering. Marie Curie's research partner was her husband, Pierre. Marie Curie discovered radium and polonium. So we've got Pierre as her husband's name, radium and polonium. Radioactivity is defined as the spontaneous emission of energy from the nucleus of the atom. Spontaneous emission of energy from the nucleus. An element can change its identity through nuclear decay. Okay, that is literally the nucleus disintegrating or decaying, changing. Okay, again, we've come a long way from Dalton, right? Steel ball, impenetrable, nothing in there, it's all uniform. Well, now we've got positive negatives, now we've got, electrons flying around, now we've got a dense positive part, and actually that dense positive part is very formidable, but it can actually split up and naturally sort of break apart. Wow. And energy being released. And of course, this has led to, our nuclear, our nuclear industry, right? That's nuclear power, nuclear bombs. All this is like the immense energy that's released from the bonds that are in the nucleus, okay, by ripping it apart or that kind of thing. Radiation emitted from the nucleus causes changes in the nucleus. Protons are ejected from the nucleus in a process called nuclear fission. Okay, there's two processes. Fission is when you have a nucleus that sort of breaks apart and becomes, two different things. And the other one is called fusion, which is much more difficult to attain. But it's basically where you have two parts added together, two sort of nuclei, and you create one kind of supernuclei, and that is incredible. The amount of energy represented there is super incredible. So there's fission and there's also fusion. Fission is breaking apart, fusion coming together. If your bones are fused, they're stuck together, right? Fused. All right. Just a couple more things here. I think we're almost done the notes. Half-life is the amount of time that it takes for a radioactive substance to disintegrate to half of its original mass through nuclear decay. So when we talk about radioactive half-life, what we're talking about is just this. You have a compound that over time basically disintegrates from its very inmost part, and it breaks apart, and it actually becomes two different things. Okay? So uranium could break apart and become two other elements. Okay? Which is amazing. I think uranium kind of breaks apart to become thorium and helium. All right? Which is amazing, and there's lots of energy that's released there. Nuclear decay. All right, and it looks like that's the end of my notes for there. I'll just kind of double check to make sure we haven't missed anything, but that should be the notes that you have in front of you. So that's all the notes I have for you today. I would encourage you to look at chapter 4 in your text. I would also encourage you to go ahead and check my website for different videos and resources. And also, I've created 2 Kahoots. I don't know if you play Kahoot or not, but Chemistry 30 Atomic Model History number 1. Here's a little trivia for you. And there's also Model History number 2. So I've included those links on my website. Go ahead and play that. It's a good review to see how you're doing with your understanding of the model of the atom. Okay, and here's the website, www.mrmathwell.com. And of course, if you go to the Chem 30 page, you can see videos and resources there for the taking. All right, see you later.